I'm going to solve these 9 problems in the order that I've listed on the left. So with the integral of 14 times x minus 2, I always like to rewrite the problem. Here we want to use u substitution. We want to set u equal to x minus 2, meaning that du is simply dx, because when we derive, it's really 1 dx. So we can factor out the constant, because if you have a constant within the argument of the integral, you can move it to the outside. And then within the integral, we can now substitute u in, and we can substitute du for dx, since we established that du is equal to dx. Now we just integrate regularly. So the integral of u to the 6th is equal to u to the 7th over 7 plus c, since it's the indefinite integral, meaning that there's no numbers here and here. If we if we remove the 7 and divide 14 by it, we have 2 u to the 7th plus c. And then if we substitute in our u from before, it gives us the final answer of 2 times x minus 2 to the 7th plus c. Next question. As I said before, I like to rewrite the problem. We've got the integral of v plus 1 over 2v minus 11 to the 4th dv. When you have the sum, or when you have a sum within an integral, like something plus something else, you can separate it into 2 different integrals. So this is equal to the integral of v dv plus the integral of 1 over 2v minus 11 to the 4th dv. Integrating this one is easy. This is equal to v squared over 2. And now we would put plus c, because this is an indefinite integral. But when we integrate this one, it will also have a plus c. So we only need to write it once. So I won't write it until we're writing the final answer, just for clarity. Integrating this term is going to be more difficult though. First, let's rewrite this with a negative exponent. Let's write plus the integral of 2v minus 11 to the negative 4 dv. We're going to do u substitution integrate. Let's do that on the side. We're going to set u equal to 2v minus 11, meaning that du is going to be 2 dv. Let's substitute in the value of du now. So we have 2v minus 11 to the negative 4, which is just going to be u to the negative 4, and then du, which is equal to 2 dv. So this is u, and this is du. Notice though how we essentially spawned in a 2 here. Like there was no 2 in the original, it was only this and a dv, but now we have this 2 dv. To equalize that, we need to multiply by 1/2, because the 2 times 1/2 will make it into 1 and cancel each other out. And we can move this 1/2 outside of the integral, since a constant within the integral can be moved to the outside. So now if we substitute our u and du values, this becomes 1/2 moved outside of the integral, like I said before, and then the integral of u to the negative 4 du. Now this is easy to integrate. It's equal to 1/2 u to the negative 3 over negative 3 plus c. So if we multiply the negative 3, the 1 over negative 3, it becomes negative 1 over 6 times u to the negative 3 plus c. And if we substitute our u back in, it becomes negative 1/6 times 2v minus 11 to the negative 3 plus c. Now let's bring everything together. recall our first integral, which was the integral of v. Let's bring this down. So we've got v squared over 2, which was the integral of v. And then let's add this part, minus 1/6 times 2v minus 11 to the negative 3 plus c. On to question 3. So the integral of x squared over x minus 10 dx. When you have x squared over a binomial being a term with an expression with two terms, x being one and negative 10 being the second, usually the easiest course of action to integrate is to first do polynomial division. So let's do that here. We've got x squared divided by x minus 10. I have a separate YouTube video on how to do polynomial division, so I'll run through this kind of quickly. If you want a more thorough explanation, just head to that video. But I'll explain it here. So we've got x squared. Now, the first thing to do is write a minus sign and a parentheses. Now we need to think, x times what is going to bring us to x squared? X times x gives us x squared. So now we write x up here, and then we multiply x times x, which is going to give us x squared in the parentheses that we wrote before, the minus parentheses. And then negative 10 times x is negative 10x. We're going to write that here. Now we subtract this binomial from the original x squared, which gives us 0 plus 10x. So we can erase the 0 and the plus for clarity. And I'll make the 0 a little neater. Now we need to think x times what is going to give us 10x. The answer is positive 10. So let's write that, plus 10. We write that up here. So now, just as we did before, let's write the minus and then parentheses. Now let's multiply x times 10, and write that here, 10x, and then negative 10 times 10, which is negative 100, which when we do this subtraction, since a negative and a negative becomes a positive, it leaves us with only positive 100. Now, instead of multiplying by 100 over x to give us 100, we are just going to call this the remainder. This gives us the final answer of x squared divided by x minus 10 is equal to x plus 10, remember from up here, plus 100 divided by x minus 10. The 100 being the remainder, and then we're dividing by what we divided by before, x minus 10. This is the quotient when you do polynomial division here. Now recognize, since these are equal, instead of integrating this, we can integrate this. So our integral becomes and remember, this is equal to what we had before. This equals that. They're equal. And recognize how this is much, much easier to integrate than what we had before. So for clarity, I'll separate each of these terms since it's a sum, and you can separate it in integrals into 3 integrals since there's 3 different terms. So this is equal to the integral of x dx plus the integral of 10 dx plus the integral of 100 over x minus 10 dx. The integral of x is simply x squared over 2. And since it's an indefinite integral, we can put plus c here, but each one of these would have a plus c, so I'll only write one plus c at the end, since that's all you need to do. Just remember to do that. Plus the integral of 10 being 10x And then the integral of this here, or let's just write plus c, since we're going to alter this. We can write plus 100, since we'll factor out the 100, times the integral of 1 over x minus 10 dx. To integrate 1 over x minus 10, let's do this on the side. Let's do u substitution. Let's say u equal to x minus 10, meaning du is equal to 1 dx. Now we can substitute in u and du. So this becomes the integral of 1 over u du. Notice how this is equal to ln of the absolute value of u plus c. This means that our integral comes out to the ln, the absolute value of x minus 10 plus c. So when we bring everything together, it becomes, and again, I'll write the plus c at the very end. It becomes x squared over 2 plus 10x plus 100 ln x minus 10 plus c. All right, question 4. The integral of x times cosine of 2 pi x squared dx. And this is the argument of cosine. Now this looks rather intimidating, but we can simply do u substitution here. We can let u be equal to the argument of this cosine, which is 2 pi x squared, meaning that du is going to be 2 pi 2x. The 2 pi stays, since when integrating, constants remain the same. And remember, pi is simply a constant. So this is equal to 4 pi x dx. We can set this equal to the integral of cosine 2 pi x squared. And now let's plug in du. But wait, now we're multiplying by an additional 4 pi to the original x and dx. Because we can't just spawn in something else to multiply by, we need to also multiply by, let's draw a line there, 1 over 4 pi, which we can move outside of the integral. So now let's substitute in u and du. This is equal to 1 over 4 pi on the outside of the integral. Since we can move constants to the outside, all we did is move this here, since you can move constant terms to the outside of the integral. And then we have the integral of cosine of u du. This is simply 1 over 4 pi times the sine of u plus c, which is sine of 2 pi x squared plus c. Next problem. We got the integral of 110 divided by e to the negative x plus 1 dx. As our first step, let's bring the 110 outside of the integral. Now this may look a little intimidating, but let's write e to the negative x for what it actually is. 1 over e to the x plus 1. You can now see that we have a fraction in the denominator of a fraction. So to remove it, let's multiply by e to the x over e to the x. And that's within the integral. So this becomes 110 times the integral of e to the x in the numerator, since we did 1 times e to the x, divided by 1 plus e to the x. And that's because we did 1 over e to the x times e to the x, which is just 1, That's where this one comes from. And then plus 1 times e to the x, which is just e to the x dx. Now this is a lot easier to integrate. We can simply do u substitution by letting u equal 1 plus e to the x. So du equals only e to the x dx. So our integral becomes du over u, which I like to write as 1 over u du. Now remember, the integral of 1 over u du is equal to ln, absolute value of u plus c. So we can rewrite this as 110 times ln of the absolute value of 1 plus e to the x, since that was our u, plus c. But 1 plus e to the x is always going to be positive, since e is just a constant, and regardless of what exponent you put it up to, it will never be negative. It will just become a really small positive number, which added to 1 will never be negative. Which is why we can remove the absolute value brackets and make this just parentheses. Next question. We have the integral of 9 tan x times ln of cosine x dx. First, let's bring the 9 outside of the integral. Our next step is to use u substitution, but it may not be immediately obvious. Let's set u equal to ln of cosine x. And the reason we're doing that is, remember, the derivative of ln u equals u prime over u, which is the same as 1 over u times du dx. So this means it's just the derivative of whatever u is divided by u. So now let's get du, which is going to be equal to u prime, which is just the derivative of cosine x, which is negative sine x, divided by u, which is just cosine x. We're going to have dx. Notice that this is equal to negative tangent x dx. And before, remember, we have a tangent within the integral. So now we can set this up as this being the u and this being du, except we'll have to bring the negative outside. And by that I mean, if we substitute in du and u, so we'll just leave u as ln cosine x for now, and we substitute in du, notice how this is exactly the same as our original expression, with the exception of tangent in our new one being negative. So to counteract that, we need to multiply by negative 1. And we can bring this negative 1 outside the integral and multiply it by 9 to give us negative 9. At this point, we can substitute in u and du. So we'll get the integral of u du. Simple as that. And now we can easily integrate u. So this becomes negative 9 times u squared over 2 plus c, which, since our u is ln cosine x, becomes negative 9 times ln cosine x squared over 2 plus c. Next question. So we have the integral of 2 divided by cosine theta minus 1 d theta. This is the same as dx, but instead of having our argument as x, it's theta, so d theta. First, let's bring the 2 out of the integral to the outside. We want to remove trig expressions in the denominator, and the easiest way to do that in this case is going to be to multiply by the conjugate, which is cosine of theta plus 1 over cosine theta plus 1. This is just something that you need to remember when you see problems of this archetype. So now, when we multiply, we'll have cosine theta plus 1 in the numerator. So if you just did 1 times cosine theta plus 1, divided by cosine squared theta minus 1 in the denominator, when we multiply cosine theta minus 1 and cosine theta plus 1. Now notice we can use the Pythagorean identity to convert this expression into a different trig function. So let's write out sine squared theta plus cosine squared theta equals 1. So if we want it to be minus 1, let's move the 1 to this side. Minus 1 equals, and let's move the sign to the other side, making it negative. So it equals negative sine squared theta. All we did was add negative sine squared theta to this side and this side. So this becomes 2 times the integral of cosine theta plus 1 divided by negative sine squared theta d theta. We can break this into two different functions. So let's do that. This will become 2 times the integral of cosine theta over negative sine squared theta d theta plus 2 times the integral of 1 over negative sine squared theta d theta. Now, for this integral, let's bring the negative 1 outside, making this negative 2 times cosine theta sine squared theta d theta. But for this one, let's leave the negative in, because this will become negative cosecant squared theta d theta. I left the negative with cosecant squared theta because if you remember, the integral of negative cosecant squared theta is cotan theta. That's just a trig identity that you should remember. A trick I use to remember the trig identities is I write out secant, secant, tan, cosecant, cosecant, cotan, but the middle cosecant is negative. The integral of negative cosecant squared theta, and that's when we multiply these two, which are next to each other, is equal to cotan theta. And similarly, the integral of negative cosecant theta times cotan theta is equal to cosecant theta. So the integral of these two multiplied to each other is this, and then the integral of these two multiplied to each other is this. And the same goes for the top with secant and tan. The integral of secant times secant, which is secant squared, is equal to tan theta, and the integral of secant theta tan theta is equal to secant theta. So just remember, when you multiply two that are next to each other, the integral of them, or the integral of that product, is equal to the one remaining in the row. Anyway, let's get back. So to integrate this, we can just do a simple u substitution by setting u equal to sine theta, meaning du is cosine theta. So when we bring this down, it becomes negative 2 times the integral of du over u squared, which is equal to negative 2 times u to the negative 2 du. We can easily integrate this, and it becomes u to the negative 1 over negative 1 plus c, which is just 2 times u to the negative 1 plus c, which is 2 to the sine theta negative 1 plus c. And remember that sine to the negative 1 is just cosecant. So this becomes 2 cosecant theta plus c. When we bring everything together, our final answer is 2 cosecant theta plus 2 cotan theta plus c. Next question. So when you have an integral and you have a square root in the denominator, these are the three identities that you should immediately think about. We're going to try to fit what's under the radical here into the formula for one of these identities. We have the integral of 28 divided by the square root of 18x minus x squared dx. First, let's bring the 28 outside of the integral, which gives us 18x minus x squared dx. And with these types of problems, when there's a radical in the denominator, and specifically what seems to be, or what can become a quadratic, we want to make this into an actual quadratic of the form ax squared plus bx plus c. So let's bring out what's under here, 18x minus x squared, and let's try to make it into a quadratic. First, let's factor out a -1 so that we can get this to the front and have it be positive. So x squared minus 18x. And now we want to complete the square to make this into a quadratic. To do that, we divide this term by 2, the b term by 2, and then square it. But now that we've added the 81 in here, realize that we've actually subtracted 81 from the entire equation, since there's a negative out here, so this is really negative 81. To balance the equation, since we can't just subtract 81, we need to add 81 as well. So this becomes 81 minus, and then this quadratic, which we can collapse into x minus 9 squared. And that's just a formula. Now let's put this under the radical. Now let's look back to our inverse trig formulas. This fits the arcsine formula. We can set x minus 9 equal to u, and we can set 9 equal to a, since a squared is 81. Nine squared minus x minus 9 squared dx. So from our trig formula, we can set a equal to 9, u equal to x minus 9, and du simply equals dx. So 9 is a, x minus 9 is u. This means that we can substitute an arcsine of u over a, which is x minus 9 over 9 plus c. This is the final answer. Now question 9, the final question of this video. Congratulations if you've made it this far and know how to solve all the previous types of questions. So we've got the integral of 1 over x squared minus 8x plus 35 dx. And just like the question before, when we have a quadratic in the denominator, we want to think about the arc trig functions. Here are the 3 functions that we'd be working with. Notice how there is not a radical, so let's try to fit this into the arctan formula. To fit this to the arctan formula, let's separate the x's from the constant, which is 35. So we've got x squared minus 8x. Let's collapse this by completing the square. So let's divide -8 by 2 and then square it. So -8 divided by 2 is 4. Squared is 16. This becomes plus 16. And since we have a plus 16 here, let's just take the 16 from the 35. So 35 minus 16 is 19. So notice how the equation is the same as before, but we've broken 35 into 16 and 19. We can now collapse this quadratic into x minus 4 squared plus 19. Now we can set u equal to x minus 4, so du is just dx, but we have a 19 here, and we're so close to fitting this to the arctan formula since we have u squared already, and du, which is, we can just put dx up here, but we need a squared. To get a squared, we're going to do the square root of 19 squared, since this is just equal to 19. So now, in addition to u and du, we have a as the square root of 19. Finally, we can Now I use the trig formula, arctan, and set this to 1 over the square root of 19, since the formula says 1 over a, times arctan x minus 4 over the square root of 19 plus c. Here's the work for the 9 questions I solved in this video. If you have any questions, leave them in the comments and I can do one of these questions or a similar one in more depth.